Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on numerically evaluating Airy functions. In the previous tutorial, we saw how to directly solve the differential equation using the initial conditions for the Airy function of the first kind and the Airy function of the second kind. And we saw that it can provide us good results, but it's not a very efficient approach. So in this lecture, I'm going to use the indirect approach, which means, as I mentioned, when we look at the Airy functions, we see that for negative x values, they have oscillatory behaviors, and for positive x values, they have exponential behavior. And this is very similar to the behavior of the Bessel functions, which was oscillatory, and the modified Bessel functions, which was exponential decay and growth. So we are going to use and take advantage of the connection of the Airy functions to the Bessel functions and the modified Bessel functions. So for positive x, the behavior of the Airy functions is exponential, growth and decay, so they are related to the modified Bessel function. For x negative, the behavior is oscillatory, so they are related to the ordinary Bessel functions. All right. And we already saw that we can directly use the solution of the ordinary differential equation. We transform this second order differential equation into a system of two ordinary first order ordinary differential equations. So y prime is u is our auxiliary function, and then u prime is xy, and we saw how to convert how to set up the function for these two equations, and then set up the ODE system solvers for the AI and BI based on the respective initial conditions, AI is 0 and BI is 0. And then so we already developed efficient ODE solvers, and then we use a system solver to solve a second order differential equation. And I used a fourth order Runge-Kutta sequence. And then AI drops rapidly for x greater than 0. So we can say after x greater than 6 or 7, AI is basically 0. And the benefit of this approach was it immediately gives us both the Airy function and its derivative, right? That's the benefit of solving this system of ordinary differential equations, because we immediately solve for both y, which is the Airy function, and u, which is here is our auxiliary function, or y prime, right? And then this was the example that I discussed, and we saw that this provides good results in terms of oscillatory behavior for negative x, and then exponential behavior for positive x. And then however, it was not efficient. So in the indirect approach here, I'm going to use the connection to the Bessel functions or modified Bessel function. So for positive x greater than 0, Airy functions are related to the modified Bessel function. And here's the relation. We define this auxiliary variable zeta, which is 2/3 x to the power of 3 over 2, right? So this is basically x square root of x, all right? And then ai of x, this is the Airy function of the first kind, is 1 over pi square root of x over 3, the modified Bessel function of the second kind, k, with the parameter or order of 1/3, and this is a function of zeta, not x, all right? So ai at x is 1 over pi square root of x over 3, k 1/3 zeta, and zeta is 2/3 x square root of x, all right? And then ai prime is minus 1 over pi x over square root of 3, k 2/3 of zeta. So this is a closed form equation. This is exact. This is not approximation. And we already implemented very efficient way of calculating k, this modified Bessel function. So here's the code. So in the Airy function class, I create two instance variables. One is the Bessel function, the other one is modified Bessel. And then for AI positive double, which means it takes a real number, zeta is 2/3 power of x and 1.5 or 3/2, and then we calculate the square root of x over 3 divided by pi times the modified Bessel function dot k nu. The new parameter or the index of the k is 1/3, and then we evaluate at zeta. All right, so very straightforward. And then for x negative, we switch to Bessel functions instead of basically modified Bessel function. And again, you can immediately see which Bessel function it is. So we know that ai of x, it has an exponential decay behavior, and this was the behavior, if you recall, this was the behavior of the modified Bessel function of the second kind, or the or basically the k function here, right? So k nu, modified Bessel function of the second kind, it has an exponential decay behavior. So that's very easy to remember for Airy function. So it's related to the k, and for x negative, it's oscillatory. So it's already, we know that it's already related to the j Bessel function of the first kind. So how do we calculate it for x negative? Again, we define this zeta parameter, but we use minus x or absolute value of x. So make it positive 2/3 of minus x to the power of 3/2. So this zeta parameter is always positive. All right. And then ai of x is square root of minus x. Remember, x is negative, so minus x is positive. Square root of minus x over 3, j of 1/3 of zeta plus j of minus 1/3 of zeta. And remember that for non-integer index or non-integer parameter of the Bessel function, j nu and j minus nu are linearly independent, right? So the sum of the two is not 0 or anything. These two are not related to each other. And for ai prime, we end up with minus x over 3 j 2/3 of zeta minus j minus 2/3 of zeta. All right. And again, in order to find a prime, we use the relations that we had for Bessel functions and the derivatives of the Bessel functions. Let's see if I can find it here. So the derivatives of the Bessel function. So if ai is j 1/3 plus j minus 1/3, and then you can take the derivative and write the derivatives of the Bessel functions in terms of x j nu minus 1 minus nu j nu over x, and then we can come up with that relation. So you combine that with these recursions, and we can prove the relations that govern the derivatives of Bessel functions. All right. So you take this equation, take the derivative, you end up with this. And the implementation is extremely simple. ai negative with a double parameter, right? So x equals negative x. So x, we know that x is negative. So I calculate negative x, so it becomes positive. And then zeta is 2/3 of power x 1.5. And remember, this x is actually this negative x here. And then we return the square root of x, which is x here is negative x over 3 times Bessel dot j nu 1/3 and zeta plus Bessel dot j nu minus 1/3 and zeta. All right, this is very easy. And now and these two are private methods, so we don't want to expose them to the user. We only want to expose this method ai double x to the user. So if x is positive, we return ai positive double, right? So this equation, if x is negative, we return this. If x is 0, we already know the exact value, right? So we just return the exact value. Okay, similar thing for the Airy function of the second kind, bi of x, and again the zeta has the same definition for x positive, x negative, and bi exponentially growing for positive x, so it's related to the modified Bessel function of the first kind. And it is equal to a square root of x over 3 I of 1/3 zeta plus I of minus 1/3 zeta, and then the derivative is x over square root of 3 I 2/3 of zeta plus I minus 2/3 of zeta. And the implementation is basically very simple and straightforward. This one, zeta is 2/3 power x 1.5, and then we return a square root of x over 3. This one, modified Bessel dot I nu 1/3 and zeta plus modified Bessel I nu minus 1/3 and zeta. All right. So this is the positive. For negative, again, we calculate zeta based on the magnitude of x or negative x, because negative x is positive. And bi is square root of x over 3, j minus, again, for negative x, bi is also oscillatory. So it's again related to the modified Bessel function. It's related to the Bessel function of the first kind. J minus 1/3 minus j 1/3, and the derivative is x over square root of 3, j minus 2/3 plus j 2/3. And the implementation is this. I set x to negative x, so x becomes positive. Zeta is 2/3 power x 1.5, and return a square root of x over a square root of square root of, so this x should be outside. A square root of, so x over a square root of 3 Bessel j nu minus okay, sorry, this is the Bessel function, not the derivative. So this is correct. So bi negative, this is bi, not the derivative, right? So this is this equation for negative square root of x over 3 Bessel dot j nu minus 1/3 and zeta minus Bessel dot j nu 1/3 and zeta. And again, these two are private, so we don't expose them to the user. We only expose this public method bi double x. If x is positive, return bi positive double. If x is negative, bi negative double. And if x is 0, return the exact value. All right. So here's an example which I did a comparison based on this approach, which we calculate based on the Bessel functions and modified Bessel functions with the scipy.special package. This is Airy function from 20 to minus 20, oscillatory behavior, exponential decay. This is AI prime, oscillatory decay. This is BI, oscillatory exponential growth, and then BI prime. And you see we have a very good match. And let's head to Eclipse, try to evaluate these, and then compare them with the scipy, especially in the Jupyter notebook. So here in my Eclipse, in the special underscore function project, last time we looked at this Airy function integration. Now I have this Airy function class, and we still have these exact values for AI 0, AI prime 0, BI 0, BI prime 0. And now I have two classes here, which I can define them as private. So these are private members. One is Bessel function, and the other one is modified Bessel function. And in the constructor, I just initialize them. And then I have AI negative, which is private, AI positive, and then this public method for AI. So BI positive, BI negative, and BI. All right. AI prime, so AI deriv positive, AI deriv negative, and then AI deriv. And these are basically just the equations that relate the derivatives to the Bessel functions. And then BI prime, BI deriv positive, BI deriv negative, and the BI. All right. And I haven't implemented the complex implementation of the Airy functions, but we may look at it in the next lecture. All right. So this is the class, which is very simple because we already have these implementations for the Bessel and modified Bessel. So Airy functions becomes very simple, and I have this test class here, test Airy. So let's look at test 1. So now I use my Airy function class, which uses the Bessel function relations, and I create X array, linear space minus 20 to 2, 1000. Create my timer. AI is func.ai. All right. and then I plot it. So let's look at this. Now you see the difference here. So in Airy function integration, it took about 600 milliseconds to do 1000 evaluations of the AI, but here it takes 50 milliseconds. So it's a factor of 10, 10, or it's a factor of 10 or one order of magnitude difference. And this is the reason that I always say that numerical integration is definitely not the efficient way to calculate any of the special functions. We always use power series, and if you recall, we implemented the Bessel functions and the modified Bessel functions as power series, and that was very efficient, right? So let's go from minus 20 to 20, or maybe minus 50 to 20, 30 milliseconds, even faster. And as you can see, we have this oscillatory behavior up until x equals 0, and then as at x equals 0 we get this exponential decay. So let's export to Python, test, and then let's open it in a text file, copy, and go to our Jupyter notebook and paste it. And we are plotting scipy.airy x0, and the index 0 is the Airy function, and you see we get a perfect fit. Now in the past tutorial, let me see if we have this. In the past tutorial we compared the result of Airy at minus 30, and we saw that we only had 4 decimal places of accuracy. So let's see what happens this time. Here I calculate minus 50, and let's see how many decimal places of accuracy we have now that we're using Bessel functions. 16, 188, 142, 3, 6. So we end up with 3, 6, 9 decimal places of accuracy, which is much better than 4 decimal places. And it's actually much faster to run, right? 1 order of magnitude difference, a factor of 10 or 20 difference. So using just the Bessel functions to evaluate Airy functions is a much better approach. And so here in test 2, let's look at test 2. I'm calculating BI. So this is the Airy function of the second kind. 55 milliseconds, again much better than before. And let's go all the way to minus 50. Again, you see the oscillatory behavior for negative x, and then the exponential growth for positive x. We can also export these to Python and open in the text file, copy, and then Jupyter notebook, here, paste them. So this Airy function in the scipy special, the first, it returns an array of Airy, Airy prime, AI, AI prime, BI, BI prime. So I have to set this to 2, and as you can see we get a very good fit. And let's see what we get at minus 50. So here this is 2, and let's see what value our Java implementation has. 13, 71, 50, 15, 20. So we get about 3, 6, 9 decimal places of accuracy, which is very good, very accurate. Alright, so back to Eclipse. So in test 3, I'm just evaluating AI at minus 50 and BI at minus 50, which is something we already looked at in Jupyter notebook. And we saw that we have 9 decimal places of accuracy for both of them. And in test 4, I'm calculating the derivative of AI, so AI prime, and then I'm plotting it. Let's go from minus 50 to 20. And again, it takes a very small time, 30 milliseconds to evaluate. And we see the oscillatory behavior for negative x, and then the exponential for positive x. And we can also export these to Python, open in a text file, copy, and then Jupyter Notebook, paste. So AI prime is the first index or index 1 or the second parameter or second value in this array. And as you can see, we have a good match. Let's see what we get from at minus 50. So 96, 89, 89, 83. So we get 3, 6, 8 decimal places of accuracy, which is very good. So back to Eclipse. And finally in test 5, I am calculating the BI prime, the derivative of the BI. So let's plot it from minus 20 to, let's go from minus 50 to 1, 34 milliseconds, and we see the oscillatory behavior. Let's export to Python, open in text file, and then go back to our Jupyter Notebook. And BI prime is the last element, which is the third one. You see we have a very good match. And let's look at the value of the BI prime, which is the third one. So minus 1.1453617. So we have 1, 2, 3, 6, 7, 8 decimal places of accuracy. Okay, so it's a very good implementation, very fast and very efficient. Okay. Alright, so I hope you enjoyed this lecture. There is one more function I believe left in the in our lectures on the special functions, which is a Struve function, and hopefully I'll discuss it in the next lecture. Thank you, and I'll see you in the next one.